Okay, it is Monday morning, February 22nd, chapter 21. Doing the last couple of reactions here. Homework 6 for 21 will be due on Wednesday. We'll probably finish all the reactions today, maybe, so you can get a head start on that. Quiz 5 is not posted yet. It will be later today. And then we'll move up 22. Just talking about that. We might move that up a little bit so we have a little more time to review next week before test 2, which is coming up. Test 2 will be over chapters 19 through 22. We'll have plenty of time to help out with that. Of course, we have a recitation Thursday. The TAs will be able to help you with that and review some of those things. Jeshurun, let's go up to the overhead first here. We've been doing the Wittig reaction. We did the cyanohydrin. I think there's 6 new reactions, imines and enamines. I really separate these two, even though they're both amine reactions with carbonyls. The structures give different products. An imine is very different from an enamine. And then hydration and acetals. That's getting us ready for sugar chemistry. There's some interesting reactions here, and these are new functional groups, really. An acetal is a geminal diether. So that's not a functional group we covered before, but it's kind of an extension of it. This idea of on the same carbon, there are 2 ethers coming off, okay? It's a stable structure. We can also have hemiacetals, which are monoether alcohols on the same carbon. These are really typical of intramolecular where you have an alcohol and a carbonyl within the same molecule. And that's particular to sugars. We'll see the monosaccharides, glucose. We'll show glucose and talk about it in that context, but we'll go through the reactions with the simple alcohols, ethanol and methanol with aldehydes and ketones, and show the intermediates. So some of these mechanisms will be a little complicated, but I think if you follow along today and get the key points. I'll try to compare and contrast things with what we've learned before. All of these reactions are the same, though. We're adding nucleophiles to carbonyls. So you could say all these mechanisms are the same. The consequence, of course, is, what type of nucleophile is it and what type of product is generated. I think that's the tricky part of it. So questions on this, the roadmap, I think we're good to go there. Let's look at imines first. So we're going to react an aldehyde or a ketone. And remember, we really are specific for this. Aldehydes will react more fast than a ketone. We'll get into the kinetics of it a little bit. The rate profile in accord with pH is an important thing here. But really, any aldehyde or ketone, as I show here, acetone, reacting with a primary amine. Now, I'm showing this specific one right now, ethylamine. And it's a nitrogen with a pair of electrons and 2 hydrogens. Has to have the 2 hydrogens there. Okay, that'll come out of the mechanism. The first intermediate of the mechanism was what's called a carbanolamine. And you see, we've added the nucleophile on here. You can already see how this is going to go, right? We've transferred a proton. We got to talk about that. And so now we're just down to 1 proton on the nitrogen. The nitrogen has a lone pair, and you could imagine what? Having the oxygen come off as a leaving group. Now, maybe not hydroxide. That's a terrible leaving group, we've said. But actually, under neutral or basic conditions, that is the leaving group. Okay. We'll see it works better under acidic conditions. So I'm putting up here a couple questions for you right away. What's the full mechanism? I'm just kind of giving you a hint right now. And why is it faster at pH 5? And then examining the product here, it's a carbon-nitrogen double bond, and that is the imine, right? Where we have that pi system there, and you see the carbonyl of the carbon-oxygen bond has gone away, that functional group, and now we have the new thing. And notice the nitrogen now still has its pair of electrons, but what? Both hydrogens are gone, right? So in the mechanism, we got to account for that, and the lone pair being there. All right, well, let's just go with this so far. What do we got? Let's figure out the mechanism under neutral conditions. Okay, so we're just putting the amine together with the aldehyde or the ketone. You can do that. The reaction's slower, but it does work. And what do we get? we'll get O minus up here, the result, and N ethyl, 2 hydrogens. Okay. And what's the charge on the nitrogen now? So we got to keep track of formal charges carefully, right? And that's probably the difficult thing, I think, of these mechanisms, both imine, enamine, and the acetal formation, keeping track of the details. And we don't mean to be nitpicky. We mean to be thorough enough so you understand the reaction, at least its basics. So what's our charge here on this nitrogen? Somebody's got to help me out here. That intermediate, what is it? Positive, yeah, +1. And, remind yourself how to calculate those formal charges. Here we push the electrons up here, so it's O minus, right? And that's right there. Okay, how can we get to the carbanolamine? Well, just right here. Look at that. We go right to that intermediate. Now, some of these are actually stable, these intramolecular ones. If you have an amine with a tethered aldehyde or ketone, sometimes these carbanolamines can be stable, kind of like the hemiacetals if you've read ahead. We won't worry about that yet. We'll just view the carbanolamine as what its name implies, and your book points that out. It's carbonyl alcohol with an amine on it, and notice it's geminal. It's on the same carbon. Okay. Now, how do we get to this? How do we get the double bond there? Oh, well, let's just try this under neutral conditions. Let's just push the leaving group off, right? And we'll kind of invert the structure there. Nitrogen still has that second hydrogen. We took one off here, right? So kind of keep track of all aspects of it. And then we've got our ethyl group here. And we could use any primary amine. It's got to be primary, though, just one alkyl group on the amine. It's got to have the 2 hydrogens here in order to form the amine. So we get to here, and what else do we have? Oh, well, we've got OH minus. Oh, and we need a charge here too, right? What's our charge on nitrogen again? It's +1 again, right? So you can kind of see this, yeah. But now we've got the nitrogen carbon double bond. So how do we get to the neutral imine product here? Well, we just take this and put the proton there. Okay, and that's the lone pair back. And notice we generate water. So where does the oxygen end up? It ends up as water. Now, this is actually quite slow. That's the full mechanism under neutral conditions. What's the deal with this fast at pH 5? And pH 5, is that acidic, neutral, or basic? What is that? Neutral is 7, right? So what's pH of 5? If we run this in water, slightly acidic. And how can we get this pH 5? Well, we add acetic acid. A little bit of acetic acid will make this reaction run a lot faster, or a little bit of HCl. It doesn't matter. Let me show you the kinetic profile of this reaction. So this has been measured and studied very extensively. So here's the rate of the reaction right here, going up. And here's the pH down here, pH 0, 7, and let's go up to 14 here. The whole range there, and the rate looks like this. The best rate here is at 5, which is a question mark, right? So what can we figure out here? Should we modify our mechanism? Let's see, we could bring that back down. Get that one up there. So let's see, if we are at pH 5, first of all, are we acidic then or basic? We're acidic, right? We have higher concentration of hydronium ion, or let's just say H+. How can that affect things here? Well, we could start out by protonating that. If we're acidic, there'll be a little bit more of the protonated form of the aldehyde of the ketone, right? So I'm modifying the mechanism here, and you can add in the flow of electrons to see what's going on here. So let's modify the whole thing. So here we have the amine still attacking, but now the protonated aldehyde or ketone. And what? Then we don't need to invoke this. right? We can still have the lone pair come down here and grab a proton off the ammonium. We call this protonated amine down here an ammonium, right? Because it is the protonated form of the amine, okay? It's like ammonium cation, NH4. But we've got two alkyl groups on there, but we have 4 total bonds on there. And so what, this can grab the proton off there. And then we don't have this carbonylamine now. We've got 2 groups on there. So we have hydronium. That's different now, right? And then what? We have the lone pair come in again, and then we kick off not hydroxide. What do we have come off? We have water already. Okay. And then look, water or acetate or whatever conjugate base we have from our weak acid can what? Come in and grab that off there. And so our byproduct might be more hydronium or more acetic acid. Okay. Now, why would this be faster? Okay, we modified our mechanism. What's the deal here? Is this a better electrophile now? Okay, that is our electrophile. And the slow step is actually this one right here. So by having that aldehyde or ketone protonated, is that going to make that reaction faster? Yeah, okay. We have a resonance structure here. We could just draw a resonance structure of that to this, right? OH with a plus right there. And look, that's a full plus charge now, right? So yeah, we can invoke either one of these. That's an even better representation if this is protonated. Okay. Now that's not a great base, but at acidic conditions, we're going to have more of this. Okay, so that's going to help things out here. Are there some other steps that might be helped out by having protons available? Yeah, here here I'm showing this intramolecular proton transfer. You can actually do this, have water take this off or acetate take this off, and then have the acid protonate again here. So I'm simplifying the mechanism, but having this protonate makes this what? A better leaving group, right? And so that pathway comes off there. How about this step though? Does acid help that step out? No, we got to take that off. High acid concentration would keep that protonated, right? Okay. In fact, this molecule right here has a pKa of around 5. So we have to neutralize this or make this slightly basic or to fully get the neutral thing. Or you can see if we have this super acidic, we're going to have that protonated. There's another big problem here. If we're down at pH 0 or pH 1, the reaction almost shuts off completely. It gets so slow. If all these things are good, why isn't a lot of acid better? What's the issue there? Yeah. Yeah. So the person is saying at high acid concentration, you protonate the nitrogen, and now it's what? Not a nucleophile. So let's draw that equilibrium here. If we have strong acid, then we have ethyl NH3 plus. And look, the lone pair is taken up there. So if we're too acidic, we keep that protonated and that our nucleophile goes away. You could say, right? Sure, the more acid you have, the better you protonate this and the better your electrophile is. But it's a balance, and that's what equilibrium always is, right? So this rate profile, depending on the pH, is important. You can see it expressed in the mechanism here. Question on that? Okay, let's get some other examples up here of this. And notice these will all be primary amines. How about benzaldehyde with benzylamine? So here we have a lot of aromatic groups floating around. We have an aldehyde and we have a primary amine. So what are we going to get? We're going to get the imine. Okay. And I'll just say phenyl. Okay, there. But you see, there's our imine. Okay. How about this one? And yeah, see if you can, figure these products out. Okay. How about this one? And our conditions here, if you leave out the acid, you just have a super slow reaction. So you should show a little bit of acetic acid. That'll lower the pH into that good region, 5 or so, where it's fast. So yeah, if you show a little bit of acetic acid here, that's a good thing. And then what's our imine here? The nitrogen with an isopropyl. Okay. And let's see, do I have one more? Yep. Whatever the aldehyde is, and whatever the amine is. So here's butylamine with this butanal. And what do we get? The imine with the butyl on it. Yeah. Remind yourself, there are lone pairs on there. But those are all good yielding reactions for, what do we say, the imine. Okay. All right. Let's go on to the enamine. Oh. Now the enamine, similar thing, but the name starts with an E, right? And the enamine will be a secondary amine. So here we have 2 alkyl groups on there. Aldehyde or ketone, doesn't matter. And remember, we're focused on aldehydes and ketones, not other carbonyl containing groups, okay? So it's no leaving group on the side here, okay? We're adding and then eliminating water. That's a key thing here for both of these reactions. But this is now the enamine. And, notice the combination. And again, this works best with a little bit of acetic acid. Okay, the pH profile is similar there. We're going to get similar, let's see, carbanolamine. Okay. But notice we have 2 here now. Okay. We can't, if you think about this, we could, think about forming the double bond there and eliminating water, or whatever it is, maybe hydroxide even. Okay. But let's get the full mechanism on there. But now we don't have a second hydrogen to take off. We only have the 1 hydrogen here because this is secondary. Okay. So what can we do here? Well, we need to have at least 1 alpha hydrogen. And by alpha, I mean next door originally to the carbonyl. So it's got to have 1 hydrogen next door. And then you see, what can we do? And you can already see the mechanism here, right? And we're going to go to this with the carbon-carbon double bond now, okay? And why are we doing that? Well, we're doing it mainly, why? Because it's a secondary amine now, okay? Before we got to here and we had a hydrogen, right? That was the imine. We had that second hydrogen. We don't have that now. We've got the dialkyl, and I'm going to use a term here, iminium ion. This iminium ion has the nitrogen-carbon double bond with 4 groups on nitrogen, and we actually saw it before. And we'll compare and contrast here. I'll have Jesher and go to the upper board. We'll kind of compare and contrast. In the imine up there, we saw the same iminium ion before we took the second proton off. Okay, but now down here, we've got the dialkyl. Jesher, come down here. We've got the dialkyl now from the secondary amine, and we can't easily break a carbon-nitrogen bond, okay? That would have to have an SN2 attack and break a higher energy carbon-nitrogen bond, okay? Whereas before we just did a deprotonation, which is similar, okay? But let's look at the full thing here. Let's go ahead and protonate our carbonyl. And by protonating, we're going to make that a better electrophile, right? And then nitrogen's going to attack. It is dialkyl or diaryl. It's got to have just the 1 hydrogen on it. Push the electrons up. And I think, yeah, it goes right to there. No, not quite. What does it go to? Uh, Here, let's have the whole thing here, right? It goes to the protonated carbonylamine, the two ethyls, oh, hydrogen there. Okay. And here's another thing to notice. We're under acidic conditions. That means most of your intermediates, if they're charged, will be plus charged. That's another way to check some of these complicated mechanisms. We'll see later on, if you're under basic conditions, most of your intermediates will be negatively charged. Okay, we already kind of saw that with the zwitterion, with the amino acid, when we put it at different pHs. If we're at superacidic range, it tended to be more positive overall. If we're more basic, the molecular results negative. We form the conjugate base, right? So that's kind of what that means. Here we have the protonated form. Let's go ahead and grab that proton there. And I think here we'll get to what? We get to our hydronium ion, the two ethyls on there. Okay. And now we can eliminate here. And I'll draw the two intermediates here in the resonance structure. So when we lose water there, right, we get the carbocation and the amine. And the free amine, you see, after we take this proton off, has a lone pair there, right? So we can invoke a resonance structure here. And that is, oh, that's this guy. So some of our things, just looking at the concept, are still there. So for the full mechanism. So what do we get here? Yeah, we get the aminium ion. And notice we have the plus charge on nitrogen because we use the lone pair to come and stabilize this. And these are indeed resonance structures of each other right here and here, right? And then from either resonance structure, we can then eliminate the proton. Here we're using hydroxide, and that was under the neutral conditions. But now let's just use water, okay? And we don't have a proton here to take off because it's from a secondary amine. And so when we eliminate there, what do we get? We get the double bond on the side, okay? And that's why we have to have at least one alpha hydrogen there in order to pull off. Okay, now let's contrast again. We'll make you move back and forth again, Jessica. How about up above here? Look at that same aminium ion, right? From the primary amine leading to the imine, we have that proton right there, right? Right here. And we take that off with base to go to the neutral imine, right? Because we have that secondary hydrogen there. But now coming down here, sorry, making you move all around. He's okay. We've got that similar thing here, right? We've got the aminium ion. We have two alkyls here. And the easier thing to do is to deprotonate. But now we're deprotonating at the alpha position, flowing electrons in, getting the carbon-carbon double bond. Okay. Let's look at some other examples of this. Got some more to look at. And what are we going to do here? Let me make some more room. Sorry. How about if we have this aldehyde and we have dimethylamine? What are we going to form there? Well, we're going to form the imine, enamine, carbon double bond. The oxygen's now gone, and the dimethylamine is right there. Okay. All right. How about this one? How about where we've got an isopropyl here, ketone. Oh, let's put a tert-butyl there. And how about this amine? It's called pyrrolidine. That's the secondary amine. It's cyclic, right? And what do we get here? Well, we get the double bond out here, and we get the pyrrolidine right there. Okay. Let's see. How about this one? Ketone. And, oh, how about another cyclic one? This one has an ether in it. Okay. But again, focus on what you know here. Here's a carbonyl compound with at least one alpha hydrogen and a secondary amine. So what's our product here? Well, it'll be the nitrogen compound there and the double bond over there. Okay. Question on that? Can you map onto that, all those functional groups? Yes, please. Yes. Now, sometimes you have a choice of which side to lose that second proton on, and usually it's the less hindered side. I'm not going to give you a bunch of examples where you got to do that. You'll run into some steric hindrance issues if you do it on the more hindered side. There might be some homework problems like that, but we'd point that out to you and ask you why it eliminates on one side or another. But yeah, sterics, if you make a model of some of those, they become so crowded. Let me point out some other issues here. Let's do this one. So here, is one you think this one should be fine. How about benzaldehyde and diethylamine? Well, that can add, right? It can even form the aminium ion here. But look, there's no second hydrogen at the alpha position. This position's part of the benzene ring here. You can't take off this proton from the aldehyde. You have to have another carbon here, a ketone. Acetophenone would work. Let's look at acetophenone in contrast with the same thing. Now, acetophenone with diethylamine, what will that give? That'll give this. Okay. But what happens with benzaldehyde here? It gets to the aminium ion and then it stops. Okay. It can't eliminate here, and there's no second hydrogen to eliminate there. It can't form the imine or the enamine. So what do you think occurs here? It just reverses. With water, it can just go right back. Okay. And so that's an issue. In fact, taking water out of the solution is often a way to drive this to completion. We can add a dehydrating agent or distill the water off. Again, that's an equilibrium idea that we talked about before. We talked about, how to protonate this thing and get the first couple steps to work, but overall, if these equilibriums are not favorable in the first step, if we dehydrate things and eliminate water, we can make this a favorable reaction. Okay. Question on that? Okay, one other one to look at here, kind of a difference thing. And this looks very similar, right? Acetophenone benzaldehyde. Well, there's a hydrogen, there's 3 hydrogens here. But these are different hydrogens. This is an aldehydic hydrogen, right? That's not at a position where you can pull that off and neutralize the amine. Whereas here, we can pull that proton off, you see, from this aminium ion and get the enamine easily. Okay, what if we have this? Well, if 2 ethyl groups on there is good, 3 ought to be better, right? What's the problem here? We don't have any protons to go with. That doesn't mean the first step doesn't happen. We can still do this, right? And what do we get? We can even get to this point. But look, we can never convert this back into a lone pair here unless we break a carbon-nitrogen bond. So we can't take the proton off to even form, the neutral imine, of course. And, can we lose water there? Well, maybe if we have super strong base, but then we just reverse this off, okay? So this would be completely reversible. This would just come right back off. So tertiary amine, no imine, no enamine. And you can see from the mechanism why. You don't have that second proton. You need 2 protons on a primary amine to go to the imine. And you need one hydrogen on there for a secondary amine to go to the enamine. Okay. But again, it comes out of the mechanism and seeing that, and I think that's good there. Those are the caveats there. But it was pointed out by someone, sometimes you have a choice to form the enamine on either side, and usually it's the less hindered side. Most of the time for this class, we'll give you symmetric ketones or an aldehyde where it's just one side, okay? And that hopefully will make it simpler. If it is a more complicated thing, we'd give you some hints and maybe talk about it, okay? All right, let's move on to acetals. And acetals, I like to go right to the hardest thing, okay? When we talk about acetals, we're talking about oxygen nucleophiles. And acetal, it sounds like it comes from an aldehyde maybe, or it has an acetyl group on it. Well, maybe those things, what we mean here is a geminal diether, okay? We'll also have this term hemiacetal, and this hemiacetal means a geminal ether alcohol, okay? And we'll also have this term hydrate. And a hydrate means just geminal diol. Okay. They're all kind of the same thing, oxygen nucleophiles, right? Well, why is this important, and what's up with this this chemistry here? Well, let me draw a pretty complex structure here. Talk about this a little bit. So I'm going to draw a molecule of two sugars hooked together. This is going to be called cellobiose. We'll learn more about the details of it in a later chapter. But what you'll see here is two six-membered rings hooked together. You'll see a lot of alcohols floating around here. And wow, a lot of alcohols. OH, 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 everywhere, OH. But some of the oxygens are what? Two carbons on it. So that is an ether right there. And I think part of the hard part about the sugar chemistry coming up, and acetals in general, is just identifying and getting comfortable with this new functionality, okay? We've seen ethers before. An ether means an oxygen with two carbons, okay? We've seen diethyl ether, THF, the cyclic ether, whatever. We have an ether here, and we also have an alcohol on this carbon, okay? And then let's see over here, alcohol, alcohol, secondary alcohol, primary alcohol, that's fine. None of these carbons have the ether on it, but this one right here, carbon, carbon, this is also an ether right here, okay? And then this one over here is also an ether, okay? And then alcohol, 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 alcohol. Okay, so cellobiose is pretty complicated and a lot of stereocenters. Don't worry about that yet. But just looking at the functional group. So what are we going to call this right here? We're going to call that an acetal. Okay. Okay. And what are we going to call this over here? We're going to call that the hemiacetal. Okay. And where did this come from? Let's see. We had one molecule, and this actually turns out to be glucose. We had one molecule of glucose, and glucose can have different stereochemistry at this C1 position. It's called the anomeric carbon. We'll look at that. That'll become this sugar here on the left, okay? And then let's see, this other sugar here on the right will also be glucose. Like I said, don't worry about the stereochemistry yet. But look, we're going to form our hemiacetal right here. This is the sugar here on the right. It's also a glucose. This being a nucleophile here, and then transfer the proton there. That's going to become our hemiacetal. Okay. How do we get our acetal between the two? Well, this is going to come here, and we're going to have a leaving group there. The OH isn't going to be the leaving group on its own. We can protonate that and have that come off as hydronium ion. But you can see the linkage here between the 4 position and the 1 position. That becomes our acetal. And here, just intramolecular with the same molecule here. You see this one also sitting fact, this is the product of this when it's cyclized. These are two of the same sugars coming together. And you'll see that pattern. Don't worry about it now. But all I want you to see is that this is being a nucleophile, right? And this is an aldehyde, okay? And most of the time, sugars sit like that as a hemiacetal. And it forms a six-member ring, which is stable, okay? It's entropically favored. It's in proximity. That's the term your book uses. It doesn't get into an entropy argument, but having it in close proximity means this is going to be favored, the hemiacetal. And then eventually cyclizing to form the acetal between the two, okay? So I want you to be able to look at a structure like this and identify where is the hemiacetal? Why is it called that? Well, it's an ether alcohol on the same carbon, okay? And here, this is an ether on the same carbon, okay? That's where we have the same carbon, the geminal relationships right there and there, okay? So keep that in mind. I know that's a more complicated thing. We'll leave it up here and get into these simpler guys, okay? Let's do first hydrate reactions with water, and then we'll do the acetals. And we'll just stick with simple alcohols. The mechanisms will be a little bit tricky, and that's the reason why we're going to start out first with hydrate, okay? And, you know, this seems like a big step backwards, actually. We've had water before in contact with a lot of compounds, right? So what are we talking about here with a hydrate now? Well, we're talking about a gem diol, okay? Two alcohols on the same thing. You see water being incorporated there. This is one of the world's worst reactions because it's freely reversible, and it never, hardly ever favors the hydrate unless you have electron withdrawing groups here, or unless it's small, okay? And you'll see the molecules that favor this. If you have formaldehyde, now there's a small one. At equilibrium, it's 100% the hydrate. Okay? So this is percent hydrate I'm showing. If you have acetaldehyde, it's 50%. But again, you can't isolate the acetal or the hydrate here of acetaldehyde. It will just reverse back. So this is at equilibrium in water. Okay, you can observe it's 50% the gem diol. But if you try to isolate it, it just goes right back. If you have this aldehyde, tert-butyl group over here, that's 19%. If you have acetone, now the ketones, that's 0.14%, less than 1%, okay? If you've got, with electron withdrawing groups here, trifluoroacetone, I'm sorry, hexafluoroacetone, every hydrogen replaced with fluoride, then it's actually 100%. If you have this aldehyde, trichloroacetaldehyde, that's also 100%. So what are the factors here that favor hydrate formation? Well, it's the small size. Okay, so water can get in there, big deal. If you have an alkyl group here, a lot less. If you have two alkyl groups, much, much less. And part of this is electronics. These are electron releasing, okay? The sp2 carbon is the more, oh, I drew those the wrong way. Okay, so sp3, sorry, the sp3 versus sp2 is going to be electron releasing. Yep, sorry. Donating in there, and that's an inductive effect. But you see, if you have this arrangement here, now with the fluoros, that makes this much more positive, right? Much more attractive to water. So we can already see what the mechanism might be, right? So let's get into that. Let's do the mechanism. I'm going to show you the rate profile here. Here's the rate of how it forms. And we're going to have to go 0, 7, 14 again, what the acidity state of the water is. And super fast at acidic levels and super fast at basic levels. But look, neutral, it's very slow. Okay. So can we modify our mechanism and talk about this? Let's see. How can we do the reaction under basic conditions? And this is probably the easiest one to do. We've got hydroxide. How do we get to the hydrate? Well, there's a charged nucleophile, right? And notice our intermediates are negatively charged. Okay. And then how do we get to the product? Well, transfer the proton, and we get to the gem dial. Okay. And that is reversible. We can use the hydroxide in the opposite direction, do the same thing. But you see, under basic conditions, it's going to be fast, right? Because we have more of the charged nucleophile, higher concentration nucleophile. Okay, what about acidic conditions? Well, if we have an acid available, we're going to have things protonated. So let's go ahead and protonate. And that's what we talked about with the imine and enamine, right? Very similar. So we got that. Then water can attack, right? And that will give us our protonated hydronium ion of the dial. Then how do we get to the neutral guy? Well, let me take off water. Okay. So those are two different mechanisms, right? You can see why they're both fast. Here we have a better electrophile now. Here we have a better nucleophile. But this does work under neutral conditions. Let's see. And why is it slower under neutral conditions? Let's see. Let's see. Okay. Hopefully I can do this all right. You have to organize the neutral water around us a little better. So this is neutral conditions, pH 7, we'll say. We don't have a lot of hydroxide or hydronium ion. Can we use the water just to do this? Let's see, what do we do? Okay, grab that up, and then grab that. Yeah. Okay, will that go directly to, let's see, OH? Yep. Then we'll have water here. Yep. And oh yeah, OH there. I think I did it okay. Why is this so much slower? We don't have a good electrophile and we don't have a good nucleophile. And the delta S of this reaction is very high. It has to be highly ordered. Okay. I'm sorry, very low. Disorder is delta S. So here it's a more ordered transition state with the two neutral waters. You have a small amount of hydronium ion at pH 7, small amount of hydroxide, but a lot less than the acidic or the basic condition. But you can push the electrons under neutral conditions to get it to go. All right, normally these hydrates are not isolable unless you have the trifluoroacetone or the trichloro acetaldehyde or something built into the molecule that allows you to do that. Let's look at the acetals now. The acetals are going to be different. Now we're going to have not water as a nucleophile, we're going to have the alcohols. And the products are going to be ethers, not alcohols. So there's no more protons left behind, okay? So we can take a molecule like this. Let's stick with a simple one, methanol, and treat it with a small amount of acid. And that gets this reaction to go. If you leave out the acid, a lot of times you get no reaction. You have to have the acid in there. This isn't as good a nucleophile now as water itself, but this tends to be the solvent. It's often in excess, okay? You need a lot more than just 2 or 3 equivalents, actually, to get a favorable reaction. And what this will be is this, the acetal. Now, do you see why that we're calling out an acetal? There's an ether here, and there's an ether here. It's geminal. It's on the same molecule. And now it's different than the hydrate. The hydrate, we had protons here, right? And those protons could exchange protons with water and go right back to the starting material, okay? Now, this can be the product, and it's stable under neutral, and it's stable to base conditions, okay? Acid conditions, it will go back to the aldehyde or the ketone, okay? And this will come out of the mechanism, this stability issue. Acetals are stable to neutral conditions in base, but they're freely reversible back. And you see the acid would provide a pathway back. Let's get into the mechanism, and then hopefully these aspects of the reaction will become a little more clear. So let's form our better electrophile. Okay, there's our electrophile. And what's our first step? Our nucleophile is going to be what? Methanol. Okay, simplest alcohol. Okay, this works best with ethanol and methanol. We can form these methyl and these ethyl acetals. They're very stable. They're very useful for a number of things. They're also this paradigm, this model system for sugars. Okay, so let's use the lone pair and attack here. OH, and what do we get here? OMe, proton on it. I won't keep drawing this hydrogen. This is from an aldehyde. We could do the same thing from a ketone. Again, we're going to stick with aldehydes and ketones. Okay. Now, what can we do here? Well, we've got one on there. So you see, you need at least two equivalents. Excess always works best here. Okay. And, you know, we got to get this proton off of there. I'm just going to do the intramolecular proton transfer. You could take this off with a methanol molecule and then put the proton on there. But what we're going to get here is hydronium up here. And look, oh, we're halfway there. We've got the protonated hemiacetal, actually. And maybe we can have a detour here. Let's have methanol take that one of those off. And what do we get here? We get the methyl ether. And that's going to be called the hemiacetal. Okay. Okay. But let's go on from here and have this depart. What are we going to get? We're going to get OMe with a carbocation right there. What about that carbocation? Let's see. It's from the hemiacetal. What about this carbocation? It's secondary, right? Is there a way we can make that more stable? What do we have next door to that carbocation? We have the lone pairs, right? So let's go ahead and do the resonance stabilization. And that's why sugars react at the places they do. So you've got to inspect the intermediates here and the stability of this carbocation and see why it's different than if we tried to ionize an alcohol at some other spot on a sugar. If we're at the aldehyde position, that's where we're going to get this extra stabilization. And that's where we're going to eventually form our product. Let's see if we can get to the product here now. Let's add another molecule of methanol, or our small alcohol right there, right? What are we going to get? Push the electrons back over to this oxygen. And now we got OH, ME here. Oh, we've still got the protonated form. Hydronium. Notice all these intermediates are what? Positively charged. Why? Because we're in acid, right? That's another way to look at it. And then how do we get the product? Okay, well, let's take some more methanol. Grab that proton there, and there it comes off. Let's see, where did we get rid of water? Oh, right here. Here we took off water, right? When we ionized the hemiacetal. There's where our water came off. In fact, we can think of the water being removed from the equilibrium. If this is pure methanol, now we're solvating this water, okay? And we have big excess that the molecule's seeing of the methanol. So that's effectively removing that. Or we can heat this up and distill that off, right? and remove that. Or we can add a dehydrating agent, something that sequesters water. That's another way to do it. But there is the whole mechanism. We're out of time. I can just show you real quick a couple other examples. So that's just one. Any ketone or aldehyde with methanol, ethanol, we can form the acetal. And if we let it go all the way to the acetal, we'll get a stable product. So here's another one. See if we can do that one with ethanol real quick. Excess ethanol. And we're going to add just a catalytic amount of sulfuric acid to get it to go. And how about this one? Benzaldehyde with methanol and acid. And how about cyclohexanone with that same thing? Okay, so what do? You form the full acetal using the alcohol you're given there, and it's excess, if it implied to be excess, okay? So yeah, it kind of looks like it's one equivalent here, but that's the solvent in general. Okay, there's nothing else in there, no water to begin with, okay? And then this one here would be the acetal of methanol, okay? And what would this one be? The cyclic one? Similar deal there. It'd be OME and OME. Okay, here's your bonus one. What if you had alcohol that was linked covalently together? So this dialcohol has the same two alcohols in the same molecule. This will give the cyclic form. And again, that's an acetal because you have an ether here and an ether here. So that's an intramolecular example, okay? And we'll pick it up there next time. Sorry, I went over again. Questions, come on down with them. We'll, of course, keep going on this topic for Wednesday, but we'll also be getting into chapter 22, I think, on Wednesday. So try to read ahead and get ready for that homework. So very good. Thank you. We'll see you next time.